Okay.
All right, here we go. You ready?
The broadcast is now starting. All attendees are in listen-only mode.
Hello, everybody. Thank you for attending today's webinar entitled Building a Highly Scalable Distributed Row Document or Column Store with MySQL and Shard-Query. I would like to do a little bit of housekeeping first. My name is Elisa Baum, and I'm the Director of Product Marketing here at Percona. Before we get started, could you please all raise your hand to make sure that you can hear me okay? It is located in the control panel on the right-hand side. Can you please just press? Okay, good. I see people raising their hand. Thank you very, very much. Okay. During the webinar, if you have any questions, please go ahead and enter them into the questions field in the control panel on the right-hand side. At the end of Justin's presentation today, we'll get to as many questions as we possibly can. And anything we don't get to, we will address in a blog post on the MySQL Performance blog. And with that said, I'd like to introduce Justin Swanhart, who's one of Percona's senior MySQL instructors. Justin, over to you.
Hi, good morning, or I guess good afternoon if you're coming from the East Coast. My name is Justin Swanhart. I'm going to be talking to you about mainly Shard-Query. It is my sharding toolkit for MySQL. But before we get to that, I'm going to talk a bit about why a tool like Shard-Query is needed today to help scale up OLAP, that is reporting type and analytics queries. So I maintain Shard-Query. It is a tool for accessing multiple MySQL databases in parallel. That is running a single SQL statement over multiple servers, but treating it as one big virtual server. It divides up that work via sharding, that is splitting up data between different servers, table partitioning, which is the built-in MySQL partitioning function, and specific SQL features, which we'll talk about. So the idea here is we're going to distribute the work over many machines in parallel, and the more machines we can spread the work over, the faster our queries should potentially go. It is, as I said, an open source project. You can get it at code.google.com/p/shardquery. I'm also going to talk a bit today about Flexviews. Flexviews takes result sets that is a SQL query and stores it in a table. It's like a view, but it's an actual table. And then when things change in the database, they're captured by an external change data capture tool, and those changes can be applied to the views very efficiently. So it's like a query cache that is updated based on only what changes in the database. So it is pretty useful. Code.google.com/p/flexviews if you want to check it out. It's currently in a release candidate, so it needs testing. So why are tools like these needed? So I've got a Bob Dylan quote there. If your time's worth saving, then you better start swimming or you'll sink like a stone, for the times they are a-changin'. It used to be that every 18 months or so, the speed of the CPU doubled. But that doesn't happen anymore. Now we get more cores instead. So the number of transistors in a CPU doubled every 24 months, which allowed us to double the clock speed every 18 months. But this was mostly through what we call frequency scaling. And as the frequency increases on the chip, the heat increases exponentially. And so there was a limit to the gigahertz the chips could reach. So now the speed is doubling more slowly. The number of transistors on the chip continues to double at the same rate according to Moore's law, but now the doubling in speed isn't the same because the chip's don't have the same frequency scaling. Instead, they use multiple core designs, which are much more power efficient. And you have a large number of slow cores, which use less power overall than one very fast core. Some chips, like ARM chips, may have 4 1 gigahertz cores, so fairly low frequencies on the cores. So are these new chips faster than the old chips? Well, they will be faster if your program can take advantage of those multiple cores. So traditionally, databases have single-threaded queries. So especially open source databases have single-threaded queries. So a single query can only take advantage of one core. Now the physical CPU can have many logical CPUs. The logical CPUs can each one run one thread at a time. So you take the physical CPU count, so you have 2 physical CPUs on motherboard, and those each have 3 cores, and those cores are hyper-threaded, then you'll get 12 CPU threads that can be executed at any one time in the system. And all of the work in the system, all of the threads that are running inside of MySQL, all of the threads that are running in the operating system, those are all spread across those 12 logical cores. And the operating system is scheduling work across those cores. So every program uses at least one thread, and multi-threaded programs can do a lot more work than single-threaded programs, but only if it splits the work into many threads. If it doesn't split up the work, then there's no speed up. So we're talking about tasks here. A login or a report or a query, and tasks themselves can be single-threaded or multi-threaded, and tasks can have subtasks. So we're talking about the highest level task, getting a report. That report may take multiple queries, but the overall response time to finish all of the queries for the report is the response time for the task. The response time is the time to complete the task in wall clock time, the time that actually elapsed on a clock hanging on the wall. So the response time has to include the time to complete all of the subtasks, and you must include any queue time in response time. So if you call to a call center and you wait on hold for 15 minutes and talk for 5 minutes, the response time for your call is 20 minutes. Throughput is how many tasks can complete in a given unit of time. It's a measure of overall work done in the system. So response time is the time that it takes to complete a task, and throughput are the number of tasks that you can complete in a unit of time. So they're related to each other, but they're not the same thing. Now we're worried about, or we should be worried about efficiency when we talk about a workload. We take and look at the resources that we have available. So if we have a certain number of cores available, and the amount of resources that were actually used, and then multiply by 100. So for example, if you have a CPU-bound workload with 8 cores, and you can only do the work in a single thread, then you're going to have 12.5% efficiency. But if you can do all the work in parallel in 8 threads, then you'll be 100% efficient. Now, efficiency in your application is very important, because lost time is lost money. You're paying for wall clock time. Your return on investment is directly proportional to your workload's efficiency. You've bought a server. Maybe it's sitting in your data center. You have a lease on that server, or a loan for that server. You've essentially paid for it over time, and you want to be getting the most utilization possible out of it in order to make up that investment. And you can't bank lost time. Time is money, and lost time is simply lost. And also, if you don't meet an SLA or some sort of response time objective, you've basically lost the investment in that time, and you can't get it back. So it might be impossible to get critical insights in your application. So what is scalability? So scalability is a measure of what happens when resources are added to the system. What happens to efficiency when we add resources to the system? Given the same workload, if we add resources and throughput does not increase, then adding even more resources is not going to make the system any faster, right? So if we've got 8 cores and our workload can only use a single core, it's not going to make sense to add another 8 cores. It's not going to speed up the work at all. But you do have additional resources for more concurrent tasks. So you could run more reports concurrently, but you couldn't run any one report significantly faster. So this is the traditional database scaling model. It's a connection is a thread model, and one query runs in one thread, and one query, if it is CPU bound, isn't going to be able to run faster than one single core on the system. But you can run many, many threads in parallel. Now, if when you add resources to the system, the throughput goes up, then the system can scale up to the workload. When people are asking if a system is scalable, this is usually what they want to know. They want to know is, if I add additional CPUs, or if I add additional machines to the system, is it going to go faster? Usually what people are looking for is linear scalability. That is, when I double the number of machines, do I get double the performance? And hopefully that's the answer to that is yes. But oftentimes it's not exactly linear. It's going to be close to it. Now, if we add resources and the throughput goes down, then there's negative scalability. We're probably looking at mutex contention. For modern databases, this is still the biggest contention point. All of the multiple threads that are running have to compete to hold locks on important memory structures inside of the database, like the buffer pool and the adaptive hash index. and the binary log. And these areas, which are called mutexes, can become very hot spots. And the more cores you add, the more hot those spots become. This means that you really can't scale beyond 32 to 48 cores on a single machine. So response time is very important. Throughput is important, but response time is more important than throughput. If it takes 3 days to run a one-day report, it doesn't matter that you can run lots of reports at once. If you need to get answers today about yesterday, 3 days to run a one-day report is not going to work. You're not going to be able to get the answers back fast enough. So the database is traditionally designed to handle OLTP workloads, online transaction processing. It doesn't work so well for OLAP, online analytical processing. So what's OLTP? Well, we're pretty much all familiar with it. It's going to be frequent, highly concurrent reads and writes of small amounts of data. Very simple queries, typically very little aggregation. So these small queries that are executed with a lot of concurrency naturally are going to divide the work over many cores. And so MySQL is going to scale very well up until the point where you reach mutex contention because you're running on too many cores. So particularly MySQL 5.6 is looking very, very nice for scaling up OLTP workloads. So as I said earlier, the biggest contention point is probably going to be mutex contention. And reducing that contention is the main development focus at Oracle right now and at Percona. That's where really most of the work is focused, is on reducing these global contention areas that make the database slower. Now, OLAP, on the other hand, is low concurrency reads over large amounts of data. Whereas an OLTP query will typically look at a single order or a single line on an order, OLAP query is looking for all of the orders in a day or a month or a year or even for all time. So the queries tend to be complex. There are subqueries in the from clause. The aggregation is extremely common. And star schema is very common. So this is typically a data mart that you would use with, for example, Modrian or Tableau. Oftentimes, just one big table is very common. This could represent sensor data or logs of web traffic or any other type of machine generated data. So partitioning is also very common. Typically, this is going to be some sort of sensor or log data that's generated over time, or an order history. So it typically, naturally, therefore, falls into some sort of date partitioning. Now, typically, the I/O bottleneck gets hit first because you're going to have a lot of data. However, even if all the data fits in memory, or if you get very fast I/O and eliminate the I/O bottleneck, it may still be impossible to reach your response time objective. So that if your goal is to run that one-day query in an hour, and it's currently taking 3 days, even getting all the data in memory is probably not going to get it to run in an hour. Also, MySQL only has nested loops. So other databases have hash joins. MariaDB has limited support for hash joins. But MySQL's only got nested loops, which is not necessarily great for the star schema that are common in OLAP. And once again, all queries are single-threaded. So even if you can get all the data in memory, you're still going to hit a CPU bottleneck. So you may have heard the advice that if you're going to catch a bigger fish, you're going to need a bigger boat. Unfortunately, there is no bigger boat. If you have the fastest processors available, getting the next higher model of processor is likely only to increase the number of cores, not the speed per core. So you don't have the opportunity to get anything larger. Once you're CPU bound, you're pretty much stuck. So you need to change the workload. Right? Pull out your magic wand and turn OLAP queries into something that's more like OLTP. Take those big complex queries and split them into smaller queries and run those queries in parallel. So take one workload that was highly serial and break it up into small chunks and run them in parallel, and then put the results back together so that it appears like nothing happened. This allows you to take advantage of multiple cores and spread data over multiple servers. Now, of course, doing this manually for all of your queries is not practical. Most of the sharding toolkits that are available, things like JetPants and Kubrid and Gizzard, these only do single shard queries. They can't spread queries over more than one machine in parallel. So you have to manually rewrite all of your queries to use those systems. So life sometimes gives you lemons. I didn't want the sharding lemons, so I decided to write Shard-Query. It's my lemonade factory. Right? Shard-Query is designed to transparently split up complex SQL, break it up into smaller fragments of SQL, subtasks, and run them in parallel. So transparently means either through MySQL proxy. So there's a Lua interface with MySQL proxy. It has a very lightweight Lua script, basically just copies around some JSON encoded data via Gearman. It has a web interface, so there's a REST and HTTP GUI. And if you have a PHP application that you want to integrate, it just has its own direct OO interface. And it's very simple to use. It's basically create a new shard query object and then run object query in your select query. And the results come back to you in an easy-to-process format. It has a built-in data access layer that wraps around either PDO or the MySQL functions, so you can just handle them with your normal regular functions that you're used to working with. So why not just get a different database? First off, MySQL is great, and sticking with it has a lot of pros. We know how to work with it. We get backups. It's free. The other alternatives are typically very costly or very limited. Switching to another database probably means changing the SQL dialect. And the other alternatives are typically either a proprietary RDBMS, like the ones listed there at the bottom, or MapReduce, doing something along the lines of Hadoop. And MapReduce is a very great technology, but it isn't generally designed to work like an RDBMS. There now are tools that are being built that put an RDBMS framework around MapReduce, but the techniques that Shard-Query uses are still going to be faster in a native database. So Shard-Query is going to break your big queries up into small queries. So it's trying to turn the OLAP workload into something like an OLTP workload that the database has been optimized for. These smaller queries will use smaller temporary tables. Hopefully that allows aggregation to stay in memory more so than it would otherwise, and that reduces temporary tables on disk. And parallelism reduces response time. So these small queries run in parallel, not only on a single machine, but over many machines if you have it set up that way. So parallelism comes from data level parallelism primarily. So table level partitioning, you take and use MySQL partitioning to split one big table into smaller tables internally. You can use range or list partitioning for this. So this reduces I/O because your indexes are smaller. It's basically a free level of indexing, and when you have structures like the adaptive hash index, the adaptive hash index can be partitioned on Percona server, and the index ID determines the partition. So by using table partitioning, you can get a much improved scalability of the adaptive hash index. Now, MySQL could operate on partitions in parallel. It gives a natural mechanism for parallelism, but it doesn't. MySQL does not have any intra-query parallelism, but Shard-Query does. Shard-Query uses the information schema to determine what partitions are available and automatically uses those to run queries in parallel. Of course, you can also use sharding. Its name would be quite the misnomer if it didn't work with sharding. So it primarily was first designed as a sharding tool, and I added the partitioning support on top. So horizontally partitioning data over more than one server is sharding. That is, we take one big table, like a list of orders, and we spread that out over many, many servers. So the data on each server is independent. For example, we may have all of a certain range of customers on one shard, and another range of customers on another shard, and we can operate on both of those independently because they have a shared nothing relationship. There's no dependency on both of the machines. So this is called scaling out. So overall, you send SQL into Shard-Query using one of the interfaces. That SQL gets parsed. If the query includes an equality, like customer ID equals, or customer ID in, or customer ID between, and customer ID is the shard key, then the proper shards that need to be accessed will be picked. The query won't go to all of the shards in that case. So I call this shard elimination. It's the same as partition elimination inside of the database. So this is the job of the mapper, which you can see in red in the diagram. The mapper is customizable. It uses the shard key mapper interface. So if you want to implement your own custom mapper, or you have an existing custom sharding solution, you can plug Shard-Query into it and gain the ability to run these queries in parallel over your data set. It also comes with a copy of the PHP SQL parser, which is another one of my projects. This is the most capable parser of SQL for PHP on the net, and it's actually being used by Sugar CRM, so it is pretty thoroughly tested. And then Flow, that just is splitting the SQL up into tasks and sending those tasks to Gearman. And Gearman is where all the actual work happens. The SQL is executed in parallel by Gearman workers, and then the results are coalesced and returned back transparently to the client. So if we're using a directory mapper, we have really two different types of mappers, hash mapper or directory mapper, that are included out of the box. Directory mapper is very useful because it allows us to move rows between shards and to change the number of shards. Now, moving rows between shards isn't implemented out of the box. I'm still working on that, but you can add new shards, and rows will automatically start being spread over those new shards. This works really well for machine-generated data where you're constantly generating new data. You simply just continue to add new shards as your volume of data grows. But here you can see that there are 4 records that we're looking at in the sales table, and these 4 records are stored on 2 separate shards. The 100 record and the 400 record are stored on shard number 1, and the 200 record and 300 record are stored on shard number 2, and shard number 3 is simply idle. You can see the mapping table at the bottom, which maps the customer ID in the sales schema with column value 100 to the specific shard 1. So this is very flexible, but it does add overhead if you want to look up where a particular record is and which shard it is on, because you have to go do the lookup into the directory. However, since Shard-Query focuses on OLAP, you want to have your data sharded in such a way that you get an even data distribution, so the partition elimination isn't necessarily as important as it would be if Shard-Query was focused on OLTP. The hash mapper uses a modulus, simple hash function. So column value mod number of shards goes to the shard ID. If your shard key is a string, it will be a CRC32 of the string modulus the number of shards, which may not result in the best data distribution, but you can change that because the shard key mapper is extensible if you don't like that. But here you can see all 3 shards are used because there is no possibility to map rows to individual shards. It's a fixed mapping based on that math function there, column value mod number of shards. So your number of shards are fixed. You cannot add or remove shards. So this really isn't the best way to go about things. But if you want to work on a small data set and you're going to throw it away, or other various scenarios, you might choose to use the hash mapper. So what about unsharded tables and joins? So tables that don't contain the shard key, in this example I gave, customer ID, the rows that don't contain that column get copied to all of the shards. So there's some redundancy in the system. This allows you to join between those sharded and unsharded tables. Those unsharded tables are typically going to be small lookup tables. We'll call them dimension tables. So this means that we're really working best for star and snowflake schemas, or simple master detail relationships. Most open source BI tools use Mondrian, and Mondrian works very well with a star or snowflake schema. As I said before, not just for sharding. You can use partitioning or sharding or both, or actually neither. Shard-Query can still add parallelism based on some SQL language features. So in-lists and subqueries are parallelized. In in-lists, you say, customer ID in 1, 2, 3. That's the same as 3 queries. Customer ID equals 1 union, customer ID equals 2 union, customer ID equals 3. Hence, all 3 of those queries can be executed in parallel. Between is the same way. Between can be converted to an in-list, which can be trivially parallelized. The queries that make up union and union all can be parallelized, but the deduplication is currently single-threaded. And uncorrelated subqueries get materialized early, they're indexed, and they also, of course, run in parallel. But as I've said a number of times now, Shard-Query is not for OLTP. The parser is relatively expensive. Now for OLAP, the parsing time and overhead of creating the data syncs and whatnot is a small fraction of the overall execution time, and so the cost is cheap. However, trying to turn an OLTP workload into an OLTP workload isn't going to work. But OLTP still caps out at 32 cores, so what do? Well, as I mentioned, you can use Shard Key Mapper. You can plug that into your own app, then just send queries directly to the shard or make that transparent using the MySQL ND plugins. Then you can use the shard query when you want to run complex queries because you can use the exact same mapper since they plug together. So Shard-Query adds intra-query parallelism to MySQL. More than one thread operates on an SQL query, which results in big time speed up because the work's divided into multiple threads. You just want to make sure you distribute your data evenly for best parallelism. Now, this just visually describes why running a query in parallel is faster than running it serially. On the left-hand side, we have a very fast processor that can only run single-threaded. So every time slice, it can cover only one more piece of the board. But on the right, we have 8 lesser pieces working in parallel. And so, in 8 time slices, they can cover the entire board. Hence, they are 8x faster than a query that's running single-threaded. So, Shard-Query 2.0 is nearing beta release. I'm currently working on adding test cases. So once I complete finishing the test suite, I'm going to release Shard-Query 2.0 beta. The current version is 1.1, but 2.0 is a nearly complete rewrite. So it's been almost 2 years in the making since the 1.1 release. So 2.0 will have automatic sharding and massively parallel loading, so you can easily add new shards and spread data over them automatically, and you have to manually move records between shards if you want to. It supports complex queries, so group by, halving, limit, order by, with rollup, derived tables, that is subqueries in the from clause, union. Basically, if MySQL supports it, it's going to work with the few exceptions which are listed on the Shard-Query website. One of the major limitations is that you cannot join between tables that are sharded on different keys. That is, if you have a table sharded on customer ID and you have a table sharded on order ID, you're not going to be able to join those two tables together in the current version. But 2.5 will support that. So the massively parallel loader takes big delimited files, it splits them up into chunks, and loads those in parallel. So it can load a table very, very quickly and without producing a tremendous amount of undo due to long-running transactions. Long-running query support. If you've got jobs that have to run for a long time, a few hours, you can run them in the background and pick up the results once the queries finish. And it has DML and DDL support. So you can run insert, update, delete, and DDL like alter table, etc. SQL comes in to one of the interfaces. It is parsed into tasks. Those tasks are executed through Gearman in parallel. So the data essentially flows from the servers back through the Gearman tasks back to the coordinator, which coalesces the data and returns it to the client. Just a note on the current state of Shard-Query. It started in May of 2010. It was only a measly 270 lines of code. It didn't do a whole lot. I was the only one that was working on it, and it was really just a functional script. It was very bare bones. Now it's much more complex. 9,700 lines of code plus external framework code that's not counted in that. Full coverage of the select, including aggregate functions and custom aggregate functions. So for example, it comes with support for the percentile aggregate function, and you can add your own custom aggregate functions as well. This will be used in version 2.5 of Shard-Query to add window functions. I also just want to thank Alex Hurd. He works at Ericsson. They're currently testing Shard-Query. The REST web interface is authored by Alex, and it's ready for testing. So the whole idea here is that we can get a bunch of smaller machines that can potentially outperform a larger machine. For example, in EC2, you can get 8 M2 .xlarge machines for close to the same cost as a HS1.8xlarge machine, a very large machine with SSDs, and get more aggregate memory and CPU power. And because you're splitting I/O over 8 machines, maybe as much I/O, particularly if you use provisioned IOPS on your EBS. So you can use Shard-Query to build a distributed row store. So each shard is an XtraDB cluster. So typically, 3 nodes per shard. This gives you a completely HA sharding solution, and then you get a simple extra backup with it. You can support massive ingestion rates. XtraDB cluster supports very high insertion rate, real-time complex querying, and if you want to access OLTP on the same data, you can use Shard-Key Mapper. So all the components here are HA. Galera itself, Yearman, Apache for the web interface if you want to use that, PHP for the main query component execution, and the proxy can be run on more than one machine as well. All of this redundancy can be geographically distributed. You can still use partitioning at table level to automatically spread the work over the multiple machines. So you can horizontally scale out the shards. And you can take advantage of InnoDB compression as well. So just a quick example of the query difference. This is a simple count star on a very large table. This was Wikipedia traffic statistics. And this was looking at a count of 1 day through 15 days worth of logs from the Wikipedia traffic stats. And with one big machine, you can see that the response time got linearly worse because the query is single-threaded. But with the 8 machines, response time is still linear, but it is 16x better because we can spread the work evenly over all 8 of these machines. You can also use Infobright. So each shard is an Infobright database. If you're using Infobright Community Edition, you've got to use something like DRBD for replication. It gets you hash joins, has very good data compression, but it doesn't have any indexes. There's single-threaded loading, so you can't have more than one database on a single MySQL and use those as shards. You can't create 16 schemas and treat that as 16 shards because there's a global loader lock. And it's append only, load data in file only, so no insert, update, or delete, and no partitions. Also, as I was trying to prepare this talk, unfortunately there is a bug in Infobright that prevents Shard-Query from working with it properly. But I'm going to try to work on a workaround and talk to the Infobright people this week to see if they can fix the problem too. And finally, we can emulate a document store with MySQL. This is just kind of an idea that has been thrown around that I thought I would give just a sample implementation of. So our schema for this document store is simply an ID value, so some document ID, customer ID, order ID, and then some document, which is a JSON document that contains the schemaless data for the document. Now, if we want to find documents by the document ID, that's easy. It's the primary key. But if we want to find, all of the rows for a specific customer, for example, like how many orders were ordered by a specific customer, we're pretty much going to have to search the document with like, which is going to cause a full table scan, and it's going to be slow. Or maybe that we can find another way. So I created a function, just a MySQL stored procedure stored function that extracts a key from a JSON document. And then we can use that function in SQL to extract the data. And then we just need a way to create some sort of kind of function index for that extraction. So this is just a stored function. It's pretty simple. It just pulls out the first key in the JSON that it finds. It's overly simple, but it just worked for this demonstration. So Flexviews lets you create materialized views. These are cached views that are updated when rows changed, but the view is updated asynchronously. That is, some rows are changed, and then you have to go refresh the view periodically to update it. But you can index it. So this is the SQL that would represent the extracted version of the data. We want to pull out the order ID for the document, and then its customer ID and order date. Sorry, this is supposed to say order total as order total. I know this looks really scary. This is the Flexviews commands for creating the table that represents that SQL. It's really not that complicated. You have to create a log on the table, and then create the view, and add the columns, and add the table, and then enable it. So it took a little while to build. It's single-threaded, and the store procedure is slow. So it took a while to build, but then we can index it, and now we can use that materialized view to see how many customers or how many documents there are for a specific customer. And if we had multiple different document tables, if we had a document table called customers, we could use the same technique to extract specific data out of that and use it to join the documents together. Now, for this example, we now know how to join a particular order document to a customer document because we've extracted the customer ID from the document. And that is it. We're going to have leave it open for questions.
Hello, everyone. Just a reminder that if you do have any questions, please go ahead and enter them in the questions panel on the right-hand side of the GoToWebinar control panel. We'll give it a minute. Okay, well, Justin, I don't think there are any questions. However, if you do have any questions, please feel free to reach out to Justin. Yes, slides will be available. I am going to be sending them out in the next 2 days. Actually, you know what, Justin, there is one question that came up, if you don't mind. Can you elaborate more on how to implement this in Percona XtraDB?
Well, it just works pretty much out of the box for regular XtraDB. When you set up Shard-Query, you create an INI file that points it to the shards that you want to use, and that will take and then store the configuration inside of Shard-Query's configuration database, and it will then just be used automatically. So I'm going to work on a tutorial, which we'll be posting within the next week or two. But you can take a look at the Shard-Query wiki. There is some kind of getting started information there, which you might find useful.
Okay.
But basically, oh, sorry.
No, you go ahead. I'm sorry. I didn't realize that you were still going.
Basically, you can choose to split your data up over multiple machines, or just use partitioning. But your best results will come from splitting it up over multiple machines. I'm done.
Okay, great. Well, everybody, thank you so much for your participation today. As I said, if we didn't get to your question, Justin will address it in his blog post on MySQL Performance blog. In addition, the slides will be mailed out to you in about 2 days, so look for them on Monday. And thank you very much for your time today. Hope you enjoyed it. Justin, thank you so much.
Thank you. Bye.